we're going to use a square bottom box as our introduction to max-min problems. So I'm just going to draw this for you. So a box has a front and a bottom, and it does something like this. Like so. So the volume for a box is its length multiplied by its width multiplied by its height. And its surface area is two panels that are the width times the length, two panels that are the length times the height, and two panels that are the width times the height. So that's a box just in general. Now the idea of optimization is that when there are no constraints on this box, right, like no limitations, no information given, you can make it as big as you'd like. And the surface area required to contain that volume will just stretch and modify itself in order to make sure the volume you've set is accommodated by the walls that you need. And so that's sort of an important idea here, is that any volume, right, like whether it's a box or a can or a ball, doesn't matter what it is, if you are occupying a space, like a volume, then there is a surface area that contains that space. Something has to be the boundary between in the box and out of the box. Otherwise, the box doesn't really exist. So this little exercise here, this discipline, optimization, is about taking some sort of limit on the volume or some sort of restriction and optimizing the space that contains your volume. So the first thing that's happened here is I've talked about a square bottom box. Now it has to be a square bottom box because I have too many variables here for us in high school calculus to handle. Right, length, width, and height, that's 3. I need to trim it down to 2. So when I make this box square bottom, what I've done is I've said that the width and the length are the same. So I'm going to switch this out for a new variable, x. Every place I see a length and a width. And x, length times width would be x squared. There's an x. There's an x. And 2xh plus 2xh reduces to 4xh. Okay, so what I have then are the equations for the space within a square bottom box and the area that binds a square bottom box. So if I continue through the problem, it says a square bottom box must hold 2 liters of stuff. What is the least amount of material needed to make such a box? So first off, liters, that's a volume. So you can tell because it's centimeters cubed. So I'm going to take that number, I'm going to park it in here. 2,000 equals x squared h. Now, as soon as you put a number down on there, it has constrained the size of box you're using. I want a list of all the boxes that contain exactly 2,000 cubic centimeters worth of stuff. Well, one of them is really, really tall, but really, really thin around. Would look like a toothpaste box, right? Like the square on the bottom is very small and the box is quite tall. The other box looks more like a pizza box. The square is quite large and it is not very tall. And there's a whole list of boxes in between there, right? As the width and the height, or the width and the length of that square decreases, the height of it increases as long as we maintain 2,000 cubic centimeters of volume. So the idea is that somewhere in all of these boxes, there's a cheapest box. There's the one where this equation has a minimum. So what I'm going to do then is I'm going to look at this and I'm going to think about doing a curve sketch. I'm not going to actually do it. I'm just going to think about doing it. And the first problem with trying to sketch a surface area is that it has two variables in it. It has an x and an h. So I'm going to try and fix that using the constraint I was given about the box. So the fact that it had to contain 2,000 cubic centimeters means that the height of that box must be 2,000 divided by the area of the bottom. So I just divided both sides by x squared. That's going to allow me to substitute that value into here, so that my surface area for any 2,000 cubic centimeter box is 2x squared plus 4x 2,000 over x squared. And of course, an x over an x squared leaves a single x in the bottom. 4 times 2,000 is 8,000. Could write it like that, or you could write it as x to the minus 1, whichever you prefer. So this is a composite function. It has a piece like a parabola and it has a piece like a rational. And those two things have been added, so it's going to make some sort of wonky curve. And what I'm after is the least amount of material. So what that's implying is that if I were to graph the surface area versus x, right, the length of this box, that at some point it's high when x is small, and then it drops and it drops and it drops, and then it turns back around. So I'm after this minimum place, right? That's what it's asking. What's the least amount of material? So what's the least amount of surface area? So I'm going to skip most of the analysis, and I'm going to go straight to the max-min part. I don't care about intercepts. I don't care about asymptotes. It only asked me for the least amount of material. So I'm hunting for a minimum. That's what that word means there, min. So really, all I have to do is take this equation that would make me the sketch and skip straight to the part where I hunt for the max minimum values. And of course, max minimums were calculated by taking the first derivative. So ds by dA by dx. Bring the 2 in front. 2 becomes 1. Bring the negative 1 in front. So negative 2. So there's my first derivative. And at a maximum or a minimum point, this first derivative, which is the slope of that wonky curve, is 0. So I have this expression now, 4x, that's a negative, 8, 1, 2, 3 over x squared equals 0. I put it back into fraction notation because it's a touch easier to understand. I'm going to bring this term over to the side. I'm going to bring this x squared up. X times x squared is x cubed. And 8,000 divided by 4 is 2,000. So I will need the cubed root of 2,000. Okay, now if I were to work that out, 2,000 to the exponent 1/3 gives me 12.599 centimeters. Now, if you remember anything from grade 9, then this answer shouldn't surprise you, but we're just going to ride with it anyway. I'm going to take this number, because I have x, I need to find the value of h. So h would be 2,000 divided by 12.599 squared. That would be 2,000 divided by 12.599 squared gives me 158.74. And give me a drum roll for that. Put that in the denominator. times 2,000 gives me 12.599. So the box that holds 2,000 cubic centimeters of stuff and has the minimum surface area, so it requires the least amount of material to make, has a length and width of 12.599 and a height of 12.599, which makes it a cube. Now you did this in grade 9, right? You tried to figure out the size of the best rectangle. You may have tried to do the size of the best rectangular prism. Well, it turns out that making something a cube gives you the least amount of surface area for a given amount of volume. Well, that's a thing that we can just memorize, right? So add that to the memory banks, no problem. But we just use calculus to prove that if you have a fixed volume and you use that fixed volume to get a relationship between the two variables involved, shove that relationship into the surface area equation, you can use calculus, right, the derivative set to 0, to find the least amount of surface area required. So I'm going to take this question, I'm going to erase this for us, and we're going to change this slightly to make it a little more complicated. We're going to go with a box that holds 2,000 centimeters cubed, but has no lid. So what if it has no lid? Okay, so the art of this is taking your basic functions for the shape involved and modifying it to meet whatever wonky conditions get put on it. So this one in particular, if I take the lid off, I'm not changing the amount of volume involved. What I am changing is where the material goes. I don't have to pay for this piece of the box anymore. And that piece of the box was this one up here, a place that is x wide and x long. So area of that would be x squared. That's these things, right? Two pieces, one's the top, one's the bottom. If I take the lid out, there's now only one of those. So if I go through, 2,000 is still my volume. So 2,000 is still x squared h. So 2,000 over h is still, 2,000 x over x squared is still h. I'm still going to take this and put it into here. So my surface area is very similar. The only difference so far is I'm missing a 2 in front. So x squared plus 8,000 x to the negative 1. All right. Again, I'm trying to minimize the amount of surface area, so I'm going to take the derivative of this thing and set it to 0, because that's how we find max minimums. Derivative of x squared is 2x minus 8,000 x to the negative 2, and I'm setting that to 0 to get a minimum. Kick this over. For x squared, bring the x up. X times x squared is x cubed. 8,000 divided by 2 is 4,000. So I need the cubed root of 4,000, which will be 3 to the exponent 1 divided by 3 gives me 15.874. All right. That's different. Changing whether or not I have a lid on this box has allowed the box to be taller and still have the minimum surface area. So I'm going to take this number, I'm going to park it back in here and find h. So 2,000 over 15.874 squared equals h. So h is approximately, let's see, raise that to the exponent negative 2 times 3000. So 7.937. All right. So the new box has a height of only 7.937. This thing has gotten shorter, but wider. So if you think about how that's working, right, the box, you don't have to pay for the top anymore. So you can pour more area into the bottom without having to pay for what's over top of it. So calculus has just pointed out to you that if you don't have to pay for the box, or for the lid of the box, now you've got something that is 7.9 centimeters high and 15.8 centimeters wide. So that the new optimal box is something like this instead of being a cube. Now maybe you can spot the quick little relationship there. 17.9, if you double that, double 7 would be 14, double 9 would be 1.8, 14 and 1.8 is 15.8. These two things are, like, this is twice that. So it turns out that if you want to have the least amount of surface area with no lid, you end up generating a box that's 2 to 1. Now you could memorize that, or you can understand how this process works. If you can imagine, we could do this where the box has no lid and it's missing one of those sides. So it looks like a paper tray, right? One of those places where you sort all your bills and such. Well, there'll be rules for the relationship there, but you could either memorize those rules or you could just hack it out with calculus. So if we were to take this, remove the lid, which I already did, and remove one of these edges, well, that would change this to 3. And then I'd have a new problem. I could work it out. Maybe the box is just a piece like this with 2 flaps. Well, that would mean I'd have to take one of these off. Maybe the box has no top and no bottom, but it has all 4 sides, so it would look like this. Right? So we're just modifying these formulas in order to try and minimize some sort of criteria. Okay, so problem type number 2. I'm just going to give you the text here, and we're going to dig through it and see what we can find. So when we did this first one, you needed to have the basic volume and the surface area for the 3-dimensional shape you were working on. And that's just sort of generally true for these problems. You need to have what's contained and what contains it. So when I read this text up here, I'm looking for whether this is about a box or a can or a sphere or some combination of those shapes in order to have my equations to start with. So a square bottom stall for storing road salt looks like a box with the lid and one side missing. So if I were to just try and quickly draw that, so here's a box. Okay, so I'm missing the top and I'm missing the front. It says it's a square bottom, so that whatever length that is the same length as that, and the height, I don't know. Okay, so just geometry-wise, this is a rectangular prism. So I'm going to start with volume is length, width, height, but because it's square bottom, length and width are the same, so I get this, which is what I had last time. Surface area for this particular box, surface area is normally so a top and a bottom, a front and a back, and a left and a right side. Okay, now in this particular box, I've taken off the top, so I'm going to lose one of these. It's only one. I'm going to lose the front edge. So instead of a front and the back, I have just a back. That leaves me with the back and the left and the right sides that are the same, so I can add them together as 3xh. There we go. So I have the volume contained inside the stall, and I have the surface area where the concrete needs to be in order to make this particular shape. All right, continuing on. What is the maximum volume of salt that can be stored in a bin with 150 square meters of surface area? Okay, so I have been given a surface area. So I'm going to pop that number in here. Now I'm trying to get a volume, so I want to be able to sketch / find the max min points of this volume equation, but I have too many variables in it. I need to get rid of the h. So I'm going to adjust this one so I have the h by itself. The 150 subtract x squared is 3xh, so divide by 3. Like so. Okay, good. So I'm going to take this expression for h and I'm going to put it into my volume equation. 150 minus x squared over 3x. An x squared divides out an x in the bottom, and I'm left with x 150 minus x squared over 3. We're going to put this x into my volume equation so I can avoid some product rule, and I'll end up with 150x over 3 minus x cubed over 3. Notice that both of these things are on top of the line with the division by 3, so both of them get divided by 3. And just to save myself some heartache, 150 divided by 3 is 50, like so. Okay. So I have an expression for volume then. This is just a cubic. So cubics do this sort of thing. This one has a negative coefficient, so I guess it goes the other way. It's this kind of thing. So I'm after a maximum volume. I'm after that particular spot there. So I'm going to get that like I did with all max mins when I did curve sketching. I'm going to take the derivative of this by the variable in question. So derivative of 50x would be 50. Derivative of x cubed would be minus 3x squared, and that divided by 3 is unaffected by the derivative. Set that to 0. Divide both sides by 3, kick that x squared over. Sorry, divide both sides. 3 divides by 3 and it's gone. Kick this over. So I'm going to have to square root 50. Now, technically, it's plus or minus. So let me get the number there. It's going to be like 7.1. 7.07. Okay, so the positive answer means that this thing is 7 meters wide and this is 7 meters long. The negative answer means that this is negative 7 meters long. You can't make a geometric shape with negative lengths. So I'm just going to vanish that one because based on the context of the problem, only the positive is good. So I'm going to write that in there. Asterisk. Choose positive solution based on context of the question. Okay. Lovely. So if I've got a value for x, I should get a value for h. H would be 150 minus 7.07 squared divided by 3 times 7.07. This number squared is 50. And 3 times the square root of 50 is 21.213. 150 minus 50 is 100, and 100 divided by 21.213 is 4.714. Okay, so I have worked out the dimensions that will give me the largest volume for a surface area of 150 square meters. So I should build this thing to be 7 long, 7 wide, and 4.7 meters tall. Now if I do that, then the space inside should be the maximum volume of a stall that shape. And what did it ask me for? What is the maximum volume of salt? Well, that would be if it's full. I don't actually have that number on here. But what I do have is an expression for volume that includes the x squared and the h. So if I squared this and multiplied it by that, then I should be able to get my volume. So let me clear out some space to do that. Okay, so the volume is x squared h. My width slash length was this 707. My height is 4.71. 707 squared was 50. So if I take that number and I multiply it by 50, I get 235.70. And the whole thing was in meters squared, so this will be in meters cubed. So if I were to be able to fill that bin completely to the top with road salt, then I would be able to put 235.7 cubic meters into it at maximum. If I made it any narrower, it would have to be taller, and I would have lost some space because it's not the maximum anymore. If I'd made it taller this way, I would have lost some area in this direction, and it wouldn't be the maximum anymore. I used calculus to find the optimal dimensions, and then used the optimal dimensions to find the maximum volume. So we'll tackle this one next. The top and bottom of a pop can costs 3 times as much as the material for the sides, presumably because of the indentation on the bottom and all that exciting tab stuff on the top. Determine the dimensions that will minimize the cost of the can. Okay, so if we start with a quick picture of a pop can, 6 years of art school paying off here. Can has a top, and it has a bottom, and it has sides. So if we're talking about the cost of the can, you don't pay for the insides, right? You only pay for the material around the edges. So that means this question is really about surface area, or at least it's about surface area to start. So the surface area for a can, there's a top, pi r squared, there's a bottom, pi r squared, and then there's this edge here, and this edge has to wrap completely around that circle, so it has to match the circumference of that circle. It's 2 pi r this way times the height of the can. Okay, now to change this from a surface area equation to a cost equation, I just have to factor in the fact that the top and the bottom cost 3 times as much. Now, it doesn't specify how much that is. It's not really necessary. All I need to be able to realize is that because this is 3 times more expensive, I have to pay for it 3 times for every 1 time I buy that. And the same for the bottom here. So if I buy this times 3, this times 3, and this times 1, I will have turned this into the cost equation for this particular can. Okay, good. So 3 pi r squared and 3 pi r squared adds together to give me 6 pi r squareds. Okay, and we need a constraint on this. So pop can Volume of a pop can is 355 milliliters, which is the same as 355 cubic centimeters. So we'll pop that in for our volume. Volume of a can is pi r squared h. So 355 divided by pi r equals h, pi r squared, sorry. I'm going to drop this constraint into my cost equation. So pi divides out of pi, an r divides out an r. 6 pi r squared. 2 times 355 is 710. And there's a single r in the denominator here. Because I'm about to take a derivative, I'm going to write it as r to the negative 1. So I have an expression for the cost of this can which takes into account the fact that the top and bottom are thrice as expensive and that the volume of the can should be 355 cubic centimeters. So in order to minimize that, I just need to take its derivative. So dc by dr would be 12 pi r. Bring the negative in front. Drop this by 1, gives me r to the negative 2. Which, for convenience, I am going to rewrite now as r in the denominator. This thing should be 0 at a maximum or minimum, so I'm going to pull that over. 12 pi r. Oops. You have to write the pi. You can't just say it. 12 pi r is 710 over r squared. Pop r squared up. I get 12 pi r cubed equals 710. Therefore, r cubed equals 710 divided by 12 pi. All right, so r will be the cube root of 710 divided by 12 pi, which is approximately something I can't do with a calculator. This is 2.66 centimeters. All right, so that's my radius. In order to get my height, I'm going to pop that radius into here. So h would be 355 divided by pi times 2.66 squared. Take that number, exponent of 2 times 355. Divide by pi. Gives me 15.96 centimeters. Okay. So if the radius is 2.66 centimeters, then the actual diameter would be about 5 centimeters, which is about this. And then the height of it would be 16 centimeters, which is about this. That's getting awfully close to the actual proportions of a pop can. So by taking the top and bottom and modifying the price, I can change this in from a surface area question to a cost question. But ultimately, once you've subbed in the constraint, right, there's some relationship between the radius and the height, in it goes, and modified the surface area equation to account for the fact that some things are more expensive, the remainder of the problem is identical to everything else we've done. Take the derivative, set it to 0, and use that 0 to find the max and min points. If it happens to be a thing that has 2 variables, once you get one, you solve the other, and we're good to go. Okay, I wrote this paragraph probably 4 times, and I'm still not satisfied it explains what I want you to do. So a developer wishes to subdivide some farmland into 4 waterfront lots. Total area of land needs to be 10,000 square meters. What dimensions would minimize the amount of fence if the river binds one side? So I'm going to draw you a river I'm going to draw you some farmland. And I'm going to cut this into 4 equal sized lots. Those, that's not even close to equal size, but hopefully you get the idea. All right, so in this particular configuration, I have a length here, and I have a width here for each lot. So the idea is that the area, which would be 4 of these things, 4 lengths times widths, right? There's length times width, length times width, length times width, length times width, should add up to 10,000, which means length times width should be 25,000. Okay, I'm going to leave it at that. I've been asked to minimize the amount of fence. Well, the fence only shows up where the yellow lines are. So the fence, F for fence, would be 1, 2, 3, 4, 5 of these sections this long, and 1, 2, 3, 4 of the sections this long. I don't need any fence along the river because the river is the boundary. Also, it's hard to put fence in a river. It's not real effective. Also defeats the point of having waterfront property. Anyway, so I have something here that I'm trying to minimize. It has too many variables, like all of the problems we've done so far. So I need to take this thing, my constraint, and I need to shove it into my equation for the fence. So I'm going to make the length the same as 2500 over W. So all I did was divide both sides by W here. So in it goes, F is 5 times 2500 over W plus 4W. Now 5 times 2500 is 12,500. And the W in the downstairs is a W to the negative 1. So I turned this equation into an expression for the amount of fence I need in terms of the width of each of those lots. So I can optimize that by taking the derivative. So df by dw would be negative 12,500, w to the negative 2, which I'm going to write in the denominator. Derivative of 4w is just 4. I'm going to kick this over, because for this to be a max or a minimum, I have to make that 0. So kick this over. 12,500 over w squared equals 4. So w squared would be 12,500 over 4. Therefore, w equals the square root of, let's see, 12,500 divided by 4 gives me 3,125. So the width of each of those lots should be 55.90 meters. And if I've got the width, I can get the length by popping it into here. So the length should be times 2,500 gives me 44.72. Wow, that was terrible. Okay. So, and of course, it did ask me to minimize the amount of fence. So I'm going to figure out how much fence that was by taking my W, putting it here, and my L and putting it there. So the amount of fence would be 5 times 44.72 plus 4 times 55.9 for a total of 3,124.9 meters of fence. It feels like a lot. 5 times 40. Feels like a lot. 5 times 44.72 plus 4 times 55.9. Well, that was neat. I have no idea where that number came from. 447.2 meters of fence. Right. So again, with these optimizations, this almost ended up square. It didn't end up square completely because I didn't have to pay for the fence on the river. If I had, then this would probably work out to 4 perfectly square lots. Same process as always, though. You were given some sort of constraint, so you had to draw it first, figure out what the constraint was, find out the equation for the thing you were trying to optimize, shove this into this, take the derivative, set it to 0. Where these get tricky in a question like this is trying to translate this paragraph into a picture like so. Because sometimes you're not just using the area or volume formulas, you have to actually construct the equation yourself. Okay, so here we have the mother of cook up your own equation type problems. We have some sort of betoothed rodent here. Then its lodge is on the other side of a river, but 60 meters downstream. Now, if you happen to be a beaver, you're constantly on the outlook for things that want to eat you. So you need to know where you would have to leave the shore in order to get back to your lodge, right? Because you want it to take as little time as possible. So if I do some very rigorous scientific study to determine that a beaver can run at 3 meters per second and can swim at 2 meters per second, then this particular beaver has a problem to solve. Because if it were to run, it can run faster, but it can only run on land. So in order to get there, it would have to run all the way down and then still swim across the river. That would be at its fastest speed, though, using its fastest amount of speed for the longest amount of time. The other option would be to just leap into the water and swim straight across. That's the shortest distance, but it's slower. So that might take a little more time. So there's probably a place somewhere in between where you can take advantage of your higher speed on land and then choose to depart the land and swim along the shorter path in order to minimize your time. Now that's the mechanics of this particular question, and not all of you are beaver scientists, so perhaps this seems a bit odd, but this is really just a physics problem with some calculus thrown in. So we just need to work out the geometry, and we should be able to do this. So I'm going to pick a place on the shore, right about here. We're going to say that's where this beaver is going to depart the shore. So I'm going to give that a label. I'm going to call that X meters from where it started. So this beaver is going to run that far. The beaver is going to swim from here straight to the lodge. Now, do you notice I've drawn myself a right angle triangle? Width of that is 20. And the length here, I'm just going to leave as y for a minute. It's going to be the rest of the riverbank. So this distance then, that's the hypotenuse of this triangle. So it would end up being the square root of 20 squared plus y squared. Whatever that is. Okay, good. So if I were to actually try and get some time out of this, physics will tell you that your speed is your distance divided by your time. Therefore, your time is your distance divided by your speed. So the total time for this particular escape will be the time spent running plus the time spent swimming. So that will end up being the distance that you run, which is x, divided by the speed which you can run at, which is 3, plus the distance you can swim at, 20 squared plus y squared divided by the speed at which you swim. So that's the expression for the time. Now you'll notice, like every single optimization problem we've done, there are two variables over here, and that's problematic. So I need to have a relationship between x and y. And fortunately, from the diagram, you can see that this piece plus this piece has to add to 60. Pop that up here. So, keeping in mind that I'm going to have to take a derivative of this, I could replace that with 60 minus y, and it wouldn't be terribly complicated to take the derivative. If I put 60 minus x in here, I'm going to have a thing in a thing in a thing. It's going to balloon out to chain rule. I maybe don't want to do that. So I'm going to choose to keep y in my equation and drop the x. So the total time will be 60 minus y divided by 3 plus 1/2 of 20 squared plus y squared to the 1/2. 60 divided by 3 is 20. And minus y divided by 3 is negative 1/3 of y. Okay, so it's derivative time. dt by dy. The derivative of 20 is gone. The derivative of negative 1/3 y would be negative 1/3. Now I have a chain rule here. The half stays out in front. That's this half. So 1/2 comes down in front. Keep the guts. Reduce the exponent by 1. That's the derivative of the outside. Now I need the derivative of the inside. Derivative of 20 squared is gone. It's just a number. Derivative of y squared would be 2y. Here we go. So 2 divides a 2. That's handy. It's a max-min problem, so this derivative has to be equal to 0 at a maximum or minimum point. So if this is 0, I'll kick that to the other side, end up with 1/3 equals. And let's see what's left here. I have a 1/2. I have a y up in the numerator, and I have a square root of 20 squared plus y squared in the denominator. Okay, I'm going to bring this 3 up here and the square root over there, so I end up with square root of 20 squared plus y squared equals 3y over 2. Alright, now I've got a square root and a thing that's not in the square root, so I'm going to have to square it in order to clean that up. I'm going to erase this so I have some space. This is a lot. And this question is, this is not a testable question, but it is an excellent example of how you can use this idea of optimization and actually use it to solve a problem that somebody actually cares about. Minimizing time that you're exposed to predators is something you should probably be able to work out if it's important to you. But minimizing the time something takes is sort of fundamental to business. It's fundamental to engineering. Right? If you can get your widgets turned around in less time, that means that your machine can execute the operation more times per second. And if you can do it more times per second, then you can get more output per second. So this is one of the cinder blocks of engineering and design. Not necessarily about beavers, but about building a mathematical model and then trying to optimize it based on some criteria. Where were we? This. I'm going to square both sides. So the square root of 20 squared plus y squared squared would be 20 squared plus y squared. This side here, 3 squared is 9, y squared is y squared, and 2 squared is 4. All right. So I'm going to bring this y squared over here. It's 9/4 of y squared minus y squared. Well, 9/4 of these minus well, this is 4/4 of that. Gives me 20 squared equals 5/4 of y squared. So bring that 4 up. 20 squared is 400. 400 times 4 would be 1600. Divided by 5 equals y squared. So y is the square root of, let's see, 1600 divided by 5. 320. So y is the square root of that, 17.89. Okay. So where is that on my diagram? That's here. So I really want to know when I should leave the shore, so I need my x value. You can get that from over here. That number taken from 60 gives me 42.11. So this particular beaver should run at its faster speed for 42 meters and 11 centimeters. At that point, it should dive into the water and it should go straight for its lodge, because even though it can swim more slowly, that distance is shorter than the amount of time it would take to pull off the legs of this triangle. Whew. So there was no geometry, that wasn't a volume or a surface area or whatever. But it doesn't have to be. It can be anything that you can model with some Pythagorean theorem or some sines and cosines or a little hint of physics that you can try and optimize stuff. Okay, here's a marginally more creative geometry type problem. We're going to cut square corners from a piece of cardboard. It's 100 centimeters by 80 centimeters. And then we're going to fold up those sides to make a box with no lid. And I want to try and cut those corners so that the volume of my box is a maximum. So if I kind of draw what's happening here, I have a piece of cardboard, 100 by 80. And I'm going to cut like this. I'm going to cut here so that this part is gone. Cut here, cut here, cut here, and fold along the dashed lines. So if you can see that happening, when I fold this edge up and this edge up, this piece here is going to meet that piece here in order to form the height of my box. The length of my box will end up being the 100 centimeters I had at the beginning, less however much I cut out of this side, and less however much I cut out of that side. And my width of the box is going to be my 80 centimeters less, again, what I cut it from this side and what I cut it from that side. So as I make the box taller, which increases its volume, I am forced to make the length and the width shorter. So this process, somewhere the box is too short to be its maximum volume. But then when that height gets big enough to maximize the volume, it becomes too narrow in order. So I'm going to have a balancing out of these two effects. So I need to write some of this stuff down then. The length of this thing would be 100 minus a height of the box for here, and the height of the box here would be 2 h's. The width of the box is going to be 80 minus a height minus another height. That's 2 heights. So the volume of my box, which would normally be length times width times height, is going to end up being 100 minus 2 heights, 80 minus 2 heights, and a height. Okay, so I can either FOIL that or I can do it as a three-way product rule. I'm going to choose to FOIL it because I can. 100 times 80 is 80 hundredths. 100 times that is minus 200h. Minus 2 times that is minus 160h. Minus 2 times minus 2 is positive 4h squared. And all of that is still multiplied by a factor of h. Throw that in. 8,000h. That's 360 h squared plus 4h cubed. So I have an expression for the volume of the box that I made this way. I just need to maximize it by taking the derivative, dv by dh, and setting it to 0. So the derivative of that would be 8,000. This would be minus 720h, and this would be 12h squared. I'm wondering if I can divide 8,000 by 12. I cannot, but I can divide it by 4. So I set this to 0 and divide all these numbers by 4. I get 2,000. 720 divided by 4 is 180. And 12 divided by 4 is 3h squared. So I have a quadratic there, which I could solve with quadratic equation. So I'm going to give that a try. My height would be negative b plus or minus the square root of b squared minus 4 times the a value, which is 3, times the c value, which is 2,000, divided by 2 times the a value, which is 3. So my height will be 180 plus or minus the square root of 180 squared, subtract 4 times 3 times 2,000 gives me 8,400 divided by 6. So the positive example, square root of that plus 180 equals divided by 6 gives me 45.27 to 8 if I round properly. Or if I do the negative version, which usually gives me negative numbers, we'll see what happens here. Square root of 8,400 divided by 6. 14.72. So which one is it? Well, the math has said to you those two numbers will either maximize or minimize the volume of this box. So you have to think about which one it is. Maybe one is a maximum and one is a minimum. Maybe one is a geometrically impossible outcome. So I'm going to think about this one here, 45 centimeters. So keep in mind that h was the amount of cardboard I cut out of that, and I had to do it twice. So that's 90 centimeters worth of cardboard I had to cut out. I can get away with that on the length, but I cannot get away with it on the width. There isn't enough cardboard to do it. This is a cubic, right? Keep that in mind. And so cubics do this sort of thing. So one of these places is going to end up being like an let's see, that would be here. This came further. That's at 45. This is at 14 on the x-axis. So this one actually ends up making a minimum, and it's a funny kind of minimum. I drew it wrong there. Because as soon as I try to take 45 out of this, this side is going to flip negative. this is negative, this is positive, this is positive. I end up with a negative volume. So what I've ended up building there is an unbox. I folded the width into negative space. I wonder whatever that means. So this one here then, the 14.72, I'm able to actually do that. That would require me to take out like 29 centimeters of cardboard. There's enough to do it on this side and enough to do it on that side. So the height that actually pulls this off is that particular number. And it turned out to be the subtraction case from your quadratic formula, which is another sort of underscored reason why you always do both of them, because sometimes it is in fact the subtraction option that works for your problem. Okay, so a bit of a weird geometry example. I'm going to take a sheet of paper and we're going to roll it up into a cylinder. I want to know the largest volume of the cylinder I can make that way if the perimeter of the sheet of paper is 300 centimeters. So that has something to do with how the dimensions of this paper are arranged. So if I were to write this thing out for you, I've got a sheet of paper like so, and if I roll it up, it does something like this. Hopefully you can see a sheet of paper rolled up like that. Okay, now this edge of the piece of paper has to be the circumference of this circle. So that's 2 pi r. That means that this is 2 pi r as well. This edge of the piece of paper makes the height of my cylinder. So does that one. So the perimeter of my piece of paper then will be 4 pi r's plus 2 h's. And allegedly it's 300 centimeters, so if I pop the 300 in there, 4 pi r plus 2h, I can divide everything by 2. It's 2 pi r plus h. I'm going to leave it like that for a minute. It has asked me to maximize the volume, so volume for a cylinder is pi r squared h. Now I'm going to end up with a binomial over here, and then I'm going to have to square the r. So I'm going to choose instead to isolate h. It's just going to be easier from an algebra point of view. So kick the 2 pi over, 150 minus 2 pi r equals h. You can put that in here. 150 minus 2 pi r. Okay, so pi r squared times 150 is 150 pi r squared. Pi r squared times negative 2 pi r would be negative 2 pi squared r cubed. So I have my volume expression entirely in r. I want to maximize it, so I need to take its derivative and set that to 0. So dv by dr gives me 300 pi r minus, bring the 3 in front, 2 times 3 would be 6 pi squared r squared. Alright, so this thing is equal to 0, and I have an r in both terms, so I'm going to factor that out. I'm using it with 300 pi minus 6 pi squared r. So I have two cases. Case 1, either r is 0. Case 2, 300 pi minus 6 pi squared r equals 0. So if I bring this over, 300 pi equals 6 pi squared r. Pi divides pi, 6, 300 divided by 6 is 50. So 50 divided by pi would be the radius I should use for that particular cylinder. Okay, so I've got an r, I can get an h, so I'm going to put my, well, let's think about this for a minute. If the radius was 0, so I made this thing 0, then I don't really have a sheet of paper anymore, I have a line that's h up one side, h down the other. So if I tried to make that into a cylinder, this would end up with R being 0. So the volume of that cylinder would be 0. I suspect that is a minimum volume. Here, on the other hand, if I put R into that, let's see, H would be 150 minus 2 pi times my radius, 50 over pi. Be 150, subtract pi divides pi, 2 times 50 is 100, gives me 50 centimeters. That's going to actually have volume, and the volume would be pi times 50 over pi squared. Right, I just took this and filled in my radius, multiplied by my height. 50 times 50 is 2,500 times 150. Pi divided by pi squared, let's just write it down. Pi, and then that's pi squared. One of these divides that. So I end up with 2,500 times 150 equals 375,000 divided by pi, which is approximately 119,366 cubic centimeters. Okay. Now this answer would have been perfectly fine. You can leave something as a fraction of pi in the denominator. It's no problem. And that's a bit of a curious geometry question. I mean, why would you know the perimeter of the sheet if you didn't know the area, et cetera, et cetera, et cetera. But that's not the point. The point of this whole exercise is if you can make two things that are related to each other, right? Like the space that is contained and the space that binds it around the outside, and you can put a constraint on one thing or the other, then you've created a potential to optimize the condition that is not constrained. So even if the geometry problem is a bit weird, it is mechanically the same set of operations to go through. So you'll find in the practice problems, I've written a few for you to try. Tread with caution. Hopefully they work. I've also attached two documents that I borrowed from some universities, and I credited them appropriately. One has some excellent examples that the question is asked and it works through how to do it. The second one is a sheet of practice questions that, if you dig deeper into the document, has solutions with them. So the trick for this unit really is to just do 1,000 of these problems. They have a rhythm to them. Even though all of the setup is different from question to question to question, you inevitably have an equation that's worth something, have an equation that you shove that one into, take its derivative, set it to 0, solve for the thing it asks for. And the more of these that you do, the more you'll be able to think about how to build the equations. And that really only comes with practice. So I will set you to it. Good luck.